Okay, so there's a lot of confusion and not a lot of clarity given in a lot of textbooks and things like that about when to model a force as doing work or when to model that force as giving the system potential energy. And really the thing about this that is kind of the elephant in the room that people ignore in this discussion is that the system that you are monitoring, or the system that you clearly define at the beginning of the problem, actually uniquely determines whether you should be modeling a conservative force as doing work or modeling that conservative force as potential energy. So let's go through the same situation twice, once modeling gravity as doing external work and once modeling it as doing potential energy, and see if we can't see what the clarity is. So let's just do the old, I'm going to drop a rock. The rock is going to fall down. It's in free fall. So if the system is just the rock, which is usually how we think of it, then really it's inappropriate to talk about gravitational potential energy, because within the system, right, there's our system, is the box just includes the rock. The gravitational force is external, right? So the right way to do this problem is to do that the work is equal to the change in kinetic energy. And by work here, I mean the net work, which in this case is just the work done by friction. So we've got mg times the downward displacement is going to be equal to 1/2 mv squared at the bottom, right? So, however, actually it doesn't have to be at the bottom. For any given displacement downward, right, the force and the displacement are in the same direction, so the cosine is of 0 degrees. That's why I don't have it in this expression. This is a positive work done, is leading to an increase in kinetic energy, and I'm sort of assuming that the kinetic energy was 0 in the beginning. Now let's look at this problem again, but instead of just thinking about the rock, let's include the rock and the entire planet Earth down below somewhere. Now this downward force of gravity is an internal force, and so you would not use it in the work kinetic energy theorem. So how does this work out? Well, instead of modeling some external force doing work, we say, hey, there's some kind of relationship between the Earth and the mass. There's a conservative force there. It's called gravity. And there's some gravitational potential energy that we can approximate with this formula mgh, where h is the height of the rock above some arbitrary distance. And those are joules of energy that are stored within the system. And those can be converted. So when we're doing our analysis of where the kinetic energy comes from, we do this. We say the energy initial is equal to the energy final. That is specifically the kinetic energy in the system in the beginning plus the potential energy in the system in the beginning. That's the total initial energy. That's got to equal the sum of the final values. And this, as we'll see in a second here, is going to lead to the exact same solution. So I'm going to pick it up right here. In the beginning, the rock is up here and it has no kinetic energy, but it has lots of potential. And as it falls, it goes to it's going to be losing the potential and gaining the kinetic. So what would that equation look like? The initial energy is all potential, right? Because there's a plus 0 for the kinetic energy, and that is going to be if it goes down a height h. If it goes down to h is equal to 0, right? So over here I have a 0 because the velocity is equal to 0 initially, and over here I have a 0 because the height has gone down to 0. And so I get in the end this relationship, mgh is equal to 1/2 mv squared, with no talk of an external force doing work, but rather an internal form of energy being converted between one form and another, which allows me to use this very powerful tool called conservation of energy, right? Which is very different than the way we did it the first time,